Forget everything you thought you knew about renewable energy. We talk about solar panels and wind turbines, but what if I told you the most powerful, consistent, and massive source of clean energy on Earth is hiding in plain sight? Imagine a world powered by the ocean itself, not just its waves or tides, but the incredibly stable temperature difference between its sun-warmed surface and its icy depths. This isn't science fiction. It's the audacious plan to unlock a truly global power grid using a technology that could change everything. Today we're diving deep into the world of ocean thermal energy conversion, or OTEC, and exploring how this engineering marvel is poised to become a reality much sooner than you think. So what exactly is this hidden powerhouse? The ocean is essentially the world's largest solar collector. Every day the sun beats down, warming the surface waters, especially in tropical regions. But just 1,000 meters below, the water is perpetually frigid, close to freezing. This creates a massive temperature difference, a thermal gradient that holds an almost unimaginable amount of energy. OTEC is the technology designed to tap into this gradient. Think of it like a giant heat engine, but instead of burning fuel, it uses the ocean's natural temperature layers to generate electricity, 24 hours a day, 7 days a week, regardless of whether the sun is shining or the wind is blowing. This isn't just another renewable. It's a source of baseload power, the steady, reliable electricity that our modern world absolutely depends on. Now let's get into the science of how it actually works. The core principle is surprisingly simple and elegant. OTEC plants use a fluid with a very low boiling point, like ammonia, warms. First, warm surface water, which can be around 25 degrees Celsius, is pumped through a heat exchanger. This heat is enough to flash boil the ammonia, turning it into a high-pressure vapor. This vapor then expands and rushes through a turbine, spinning it just like steam in a traditional power plant, and that spinning turbine is what generates electricity. But here's the magic trick. To complete the cycle, you need to turn that vapor back into a liquid so it can be used again. That's where the deep sea comes in. What? Frigid water, around 5 degrees Celsius, is pumped up from a kilometer down through a second heat exchanger. This cold water cools the ammonia vapor, condensing it back into a liquid. The liquid ammonia is then pumped back to the start of the cycle, ready to be vaporized again by the warm surface water. This continuous, closed-loop process can generate power nonstop, for as long as the sun warms the ocean and the deep sea stays cold, which is to say, indefinitely. This is what's known as a closed-cycle OTEC system, the most common design being developed today. But there are other fascinating variations. There's the open-cycle system, which uses the warm seawater itself as the working fluid. In a low-pressure chamber, the warm surface water is flash evaporated into steam. This steam drives the turbine, and then it's condensed using the cold deep-sea water. The incredible byproduct of this process is desalinated fresh water, a resource just as valuable as electricity in many parts of the world. And then there are hybrid cycles, which combine elements of both open and closed systems to maximize efficiency and produce both electricity and fresh water. Each design has its own unique set of advantages and engineering puzzles, but they all share the same goal: to unlock the immense thermal energy stored in our oceans. Of course, talking about pumping water from a kilometer deep isn't a small thing. Building an OTEC plant is an incredible feat of engineering. The most critical component is the cold water pipe. This isn't just any pipe. It needs to be massive, often 10 meters in diameter or more, and stretch for at least 1,000 meters into the crushing pressure of the deep ocean. Engineers have to use advanced materials like fiberglass reinforced, plastic or high-strength composites that can withstand the immense forces and the corrosive saltwater environment for decades. Getting this colossal structure into place is a huge logistical challenge. Then you have the platform itself. Will it be a floating structure, like an oil rig, moored in the deep ocean? Perhaps a land-based plant on a steep tropical island, with pipes running down the underwater slope? Or even a fully submerged facility, quietly generating power beneath the waves? Each design requires brilliant solutions to handle everything from powerful ocean currents and storms to the slow, creeping problem of biofouling, where marine organisms grow on the pipes and reduce their efficiency. The scale of the engineering is monumental, but so is the potential reward. Let's zoom out and think about the global impact. The potential for OTE is staggering. The tropical oceans absorb enough solar energy every single day to power the entire world many times over. For island nations and coastal communities in the tropics, OTEC could mean true energy independence. Imagine a country no longer reliant on expensive, polluting imported fossil fuels. They could have a stable, local, and clean source of power which would supercharge their economies and improve quality of life. Beyond electricity, the cold, nutrient-rich water brought up from the deep can be used for other industries. It can be used for large-scale air conditioning. A process known as seawater air conditioning, or SWAC, dramatically reducing electricity demand. It can also fuel aquaculture, as the nutrient-rich water creates perfect conditions for growing valuable seafood and algae. OTEC doesn't just create power. It can create entire new, sustainable economies. But we have to be realistic. If OTEC is so great, why isn't it everywhere already? There are significant hurdles to overcome. The biggest one is cost. The initial capital investment for an OTEC plant is enormous, largely due to the complex marine engineering and the massive cold water pipe. This has made it difficult to compete with established energy sources, even other renewables. There are also environmental questions to consider. What is the long-term impact of discharging large volumes of cold, nutrient-rich water into the surface ecosystem? Could it disrupt local marine life or trigger algal blooms? These are serious concerns that require careful site selection, environmental modeling, and ongoing monitoring. Researchers are working tirelessly on these problems, developing more efficient heat exchangers, cheaper and more durable pipe materials, and designs that minimize environmental disturbance. Every breakthrough brings the cost down and the viability up, pushing OTEC closer to becoming a mainstream energy player. So, where does that leave us? As we speak, the future of ocean power is being written. Right now, in places like Hawaii, Japan, and China, pilot projects and research facilities are proving the viability of OTEC technology. These aren't just lab experiments anymore. They're operational plants connected to grids, demonstrating that this technology works in the real world. With every passing year, the technology matures, efficiency improves, and costs come down. The geopolitical implications are huge. As climate change accelerates and the need for clean, stable energy becomes more desperate, the nations that master OTEC will hold a significant strategic advantage. It offers a path to energy security and a powerful tool in the fight against global warming. The dream of tapping the ocean's depths for truly limitless, clean energy is no longer a distant fantasy. The pieces are falling into place, the engineering is advancing, and the will to succeed is growing. The journey is long, but the destination, a sustainable global power grid fueled by the ocean itself, is closer than ever. Thanks for joining me on this deep dive into the future of energy. If you found this as fascinating as I do, make sure to like this video and subscribe for more content on the incredible technologies shaping our world. What do you think is the biggest potential of OTEC? Let me know in the comments below. See you next time.